We talk about two important theorems here. So first we start with weak law of large numbers. So consider a sequence of random variables x1, x2, x3 and so on. And these are independent and identically distributed. Identically distributed means they are drawn from the same distribution. So say their density function might look like this, or their density function just might look like this. So they are drawn from the same distribution. And the expected value of x1 is mu, x2 is also mu, expected value of x3 is mu, and xn is mu. Now you define a new random variable Sn, which is just the sum of these random variables. Now notice that Sn by n is just average of the random variables. So this is just average of the random variables. So probability that the average of the random variables differs from mu, the expected value of the random variable, this goes to 0 as n goes to infinity. As you add more and more random variables and keep on defining Sn by n, so as you add more random variables, Sn by n will keep changing. But what we are saying is, as you add more and more random variables, Sn by n becomes approximately equal to mu, which is expectation of the random variable to start with. That is, expectation of the random variable is same as the mean of the population. And that is a very powerful result. Irrespective of whether the distribution is this one or the distribution is this one, we are saying that the expectation of the random variable is same as the mean. And this is important because now you don't have to integrate and you do not have to worry about the distribution. You can just keep on picking up random variables, or from a given sample you can keep on taking values and averaging them out, and more values you average out, you can be sure that you are closer and closer to the expected value of the random variable. So expected value of the random variable and the mean become very close to each other as n goes to infinity. Now this equation just follows from the Chebyshev's inequality. So notice that in the Chebyshev inequality we had that probability that x minus mu is greater or equal to epsilon, this is less than equal to variance of x divided by epsilon square. Now here x we are taking as Sn by mu, and the two results are, this mu is nothing but expectation of x here. So expectation of Sn by mu is mu. So expectation of Sn by n is mu, and variance of Sn by n is sigma square over n. And if you plug it in here, sigma square over n, you plug it in here, you get sigma square over n epsilon square. And you can see as n goes to infinity, this entire thing goes to 0. And on this side you get probability of Sn by n minus mu. So let us quickly see this. So what is expectation of Sn by n? So n is a constant, it comes out 1 by n expectation of Sn. This is equal to 1 by n times expectation of, you have x1 plus x2, and this becomes 1 by n times expectation of x1 plus expectation of x2 all the way to expectation of xn. Now this is n times mu divided by n. This is equal to n mu divided by n, which is just mu, and that's why we have expectation of Sn by n is mu. Now we talk about the variance. Now variance of Sn by n. Now n is a constant, but variance is square, and you take an expectation of a square. So this n, when it comes out, n is a constant, it will become a square. So you have variance of Sn, which is nothing but 1 by n square times variance of x1 plus x2 all the way to xn. So this is equal to 1 by n square times you have variance of x1 plus all the way to variance of xn, and this is equal to n times sigma square over n square, and this becomes sigma square over n. So this is the weak law of large numbers. So basically what it says is, if you take a bunch of random variables and find their average, this average should be close to the expected value of the random variables. Obviously all the random variables should be independent and be from the same distribution. So the probability that this average will be different from mu will go to 0 as you have more and more sample from the distribution. So this is a very important result. So basically it says that the expectation of a random variable is same as standard mean which you compute. Now we talk about central limit theorem. Central limit theorem is one of the most important results in probability. In fact, it can be said it is the most important result in probability. In fact, entire of statistics is based upon central limit theorem. So let us now understand what central limit theorem is. So consider a sequence of independent, identically distributed random variables. So again, we are drawing a sequence of random variables from the same distribution. So the density function could be somewhat like this. The density function could be like this. The density function could look like a normal distribution like this. So we could draw from any of these distributions. So all these random variables are drawn from the same distribution. So they're identically distributed and they're independent. So you know that the expectation of each of these random variables is mu. So expectation of x1 is mu, expectation of x2 is mu, expectation of x3 is mu, and so on. And the variance of each of these random variables is sigma square. So again, you define a new random variable Sn, which is the sum of the random variables you have drawn. So the central limit theorem says that, so say you have a new random variable, which is say y, which is defined as Sn minus n times mu divided by sigma times square root of n. So this y is now normally distributed with mean 0 and variance 1. So notice the power of the result. You started with any distribution. So say you started with this distribution, and then you have drawn a sample of size n. So say you have drawn sample of size 5. So you've drawn 5 values from here. You take these 5 values, n is 5, so you have S5 minus 5 times mu. So mu you already know. So mean of this distribution and variance of this distribution you already know. So this could have been done by, say, if you're a statistician, you could have just done it by observing the data. So you know the mean and you know the variance. So the random variable y is Sn minus n times mu divided by sigma times root n. So this you can define as a new random variable. So your new random variable y is, say, S5 minus 5 times mu divided by sigma times root 5. Obviously you know the number mu and you know the number sigma. So say I will write it as y5 is S5 minus 5 times mu over sigma times root 5. You know this number sigma and you know mu. Now as this, instead of 5 you can have 6, instead of 6 you can have 7, and so on. Now this y ends up lying in the normal distribution. Now that is the power of the normal distribution. So it does not matter which distribution you started with. So instead of the shape of the distribution like this, it could have been a different shape. So you could have a shape like this. So it does not matter what is the shape of the initial distribution. The point here is that if you sum up those random variables and you form this new random variable y, you should probably write it yn. then this new random variable is distributed as a normal random variable. Now that is why the normal distribution is used everywhere, because no matter what distribution is given to you, you do not know what the shape of the distribution is. You just know two things about the distribution. You know its mean and you know its variance. Just from those two things, you can come to normal distribution by summing those random variables, subtracting, and then division. You get a normal random variable. So more precisely, you can say probability that this yn, so this probability that yn is less than or equal to a. So as n goes to infinity, this is the normal distribution. So this is the distribution function for the normal distribution. So this is less than or equal to a. So you can say probability that this x is less than or equal to a. So we should write a here. And that is what this integral is. So this integral is about the normal distribution function. So this is the cumulative distribution for the normal distribution function. So now you understand why normal distribution is so often used, because you can obtain normal distribution from any distribution just by summing up the variables, subtracting something, and dividing by the variance and square root of the sample size. You end up in normal distribution.